Let's embark together on a visual journey through space and time. We are in intergalactic space, billions of kilometers from Earth. We are lost between two neighboring galaxies, our own, the Milky Way, and Andromeda, another galaxy also made up of hundreds of billions of stars. Around us, space is almost perfectly empty. For all this, we are not nowhere, a web is woven around us. It is the web of the universe itself, spacetime. This imaginary grid made up of a multitude of small particles will allow us to visualize the invisible, the geometry of the universe, and to understand its dynamics. From where we are, the grid is calm, motionless, nothing disturbs it. And if we throw a marble, it zooms straight forward, moving away through the void forever. In reality, the grid is not perfectly static. If we fast forward, we see that it drifts very slightly, like a river which flows into the stars and whose current carries everything with it. The stars, clouds of gas, and dark matter effectively distort spacetime, pulling the fabric of the universe in their direction. Very slowly, the two galaxies are getting closer, and in several billion years, long after we disappear, the Milky Way and Andromeda will eventually merge and become one. While Andromeda is getting closer, researchers discovered at the dawn of the 20th century that most galaxies actually move away as a whole. The universe is constantly expanding like a fabric that stretches. The grid swells more and more and carries galaxies away from each other. As this expansion progresses, the wavelength of their light is stretched and turns red. We know today that this expansion accelerates, stimulated by still mysterious dark energy. The expansion would have begun 13.8 billion years ago, extremely compressed, containing only a mush of fluctuating energy. The universe would have descended suddenly to reach astronomical dimensions in a fraction of a second. This is the Big Bang. What was there before that? No one really knows. Tiny fluctuations becoming gigantic would have attracted matter, condensing it into filaments, halos, then galaxies, and the Earth. Today, we live near one of these stars, the Sun. Around the Sun revolve multiple bodies, planets, asteroids, and comets, moving freely in the grid of the universe. The immense mass of the Sun curves spacetime, and the fabric of space falls towards the star, taking everything with it. This is how the planets orbit. Without moving away from the Sun, they move straight forward, but the current continuously pulls them back towards the center. To a lesser extent, planets also attract the grid of the universe in their direction. For instance, the Earth holds the Moon, its natural satellite, as well as all our artificial satellites. The International Space Station zooms straight ahead through spacetime, but spacetime is curved by the Earth and prevents it from moving away. At a faraway distance, the grid flows slowly, and an object passing fast enough would have no difficulty escaping the pull. But the closer we get to the center, the denser the flow becomes, and the more the grid accelerates. On the surface of our planet, rockets must reach a very high speed to take off from the ground and escape the Earth. The grid converges towards the center, and if we drop several apples next to each other, spacetime will bring them together in one direction and stretch them apart in the other direction. This is called tidal forces. It is the same action that the Moon inflicts on the Earth, causing movements of the water on its surface. The back and forth motion of the tides are caused by the spin of the Earth on itself. It rotates in approximately 24 hours. This motion of all its mass affects spacetime and very slightly drags the grid along with its rotation. When we drop an apple, even if it does not touch the Earth, the rotation of our planet influences it at a distance and slightly bends its trajectory and orientation. Inside the Earth, the grid continues to fall downwards. It seeks to draw everything towards the center, but the materials that make up our planet are resistant. They exert enormous outward pressure so as not to collapse on themselves. It is this pressure that we feel in our legs when we fall to the ground after a jump. At the center, the river converges, and a marble, if it could withstand the immense pressure of the Earth's core, would remain there motionless. Arriving at the center, all the particles that make up the grid continue ahead and rebound until they emerge back out from the Earth. If we could jump through the whole planet, we would come out on the other side. In 5 billion years, our star will eventually die. The sun will no longer be able to generate its pressure and resist the flow of the grid. Its core will collapse on itself, forming an extremely dense white dwarf, while its atmosphere will slowly expand into a gigantic planetary nebula. However, not all stars disappear in this way. A few hundred light-years away, another star, a supergiant, is also burning its last fuel. 20 times more massive than the Sun, its internal pressure can no longer bear all its weight. The heart collapses, and the outer layers bounce back, exploding into a supernova. The core compresses more and more until it forms a neutron star, containing the mass of 2 suns in a space just 30 kilometers across. The grid of the universe is pulled so hard that light itself is dragged along, creating strange optical distortions. A few thousand light-years away, another star even more massive is about to explode. In an instant, the core is carried towards the center, and the outer layers are violently blown away. This time, the universe is stronger. It drags the core of the star, unable to resist, towards the center where all the mass condenses within a small sphere. The universe is so curved that its fabric falls faster than light. Nothing can escape this hellish treadmill, everything is carried downwards. It is impossible to stay still or even send a signal outwards. It's a black hole. In the universe, some black holes are born near another star, and they capture its matter in the form of a very high-temperature plasma entering an orbit around the black hole. The plasma forms an accretion disk, which loses energy and spirals towards the horizon inside the black hole. Very close to the center, the flow becomes infinitely fast, and all objects are strongly torn apart. The grid stretches so violently that it separates atoms from each other and spaghettifies all bodies. At the center, our current theories do not yet adequately describe the quantum behavior of space and time. In the universe, nothing is static. All stars, more or less, rotate on themselves. When they die and their core compresses to form a black hole, their rotation accelerates like an ice skater folding her arms alongside her body. This rotation is imprinted in the very fabric of spacetime, which continues to rotate afterward. Below a certain distance inside what we call the ergosphere of the black hole, the entire grid is carried into a faster-than-light vortex, which drives bodies in the same direction of rotation. Even light is forced to rotate with the black hole. Below the horizon where the grid falls faster than light, such a black hole would have a second internal horizon where the centrifugal force created by the rotation of spacetime counteracts gravity and slows down the fall of the grid. Mathematics extends these internal horizons with white holes from which we could emerge to explore parallel universes. However, the inner horizon of a black hole is extremely unstable and probably doesn't exist. The structure at the center of a real black hole remains mostly mysterious. Finally, if 2 black holes meet, they can begin to dance, pulling each other faster and faster until they merge and form an even bigger black hole. This new black hole vibrates like a bubble and eventually stabilizes. During such an event, the entire fabric of the universe is driven by the vibration, gravitational waves more powerful than all observable stars form and escape at the speed of light, distorting everything in their path. On September 14, 2015, after a journey of over 1 billion years, one of these vibrations ended up crossing the Earth in the blink of an eye. The Earth shook by a fraction of the size of an atom, but for the first time in history, researchers had detectors to measure these vibrations. They bore witness to a cataclysmic fusion that happened more than 1 billion years ago. In 2015, a whole new field of astronomy thus opened up, gravitational wave astronomy, allowing us to probe the very structure of the universe.